All right, welcome back, guys. Before I begin, just in case it happened in my 1 o'clock class, what's going on now with Zoom? Got hung up. I had to reboot. So if that happens, I'm going to reboot, get it going again, wait a couple of minutes, and log back in. Okay, just in case, FYI. I'm going to try to do a build up. I'm going to do a backup, I should say, for Zoom. I've not had problems with it, but this is really the first time I had a challenge with it. So I might do a backup with the web, I forget the name, web, whatever it is. I've not used that. I've heard good and bad about it, but I'll see if I have a backup system. Okay, one other thing. Now, I don't have office hours. Being adjunct, we're not required, but I do have time between my two classes, Tuesday, Thursday, and I'll send an email to that between 2:30 and 3:30, one day or the other. If you need to talk to me, send me an email. We'll make arrangements, okay? And we'll do a Zoom in that time period. So I'll send an email to that effect. Okay. Where were we? We were talking about chemistry. Okay, this is the page I see that we ended up with. We were talking about the electron configuration. Now, just a quick rehash. We talked about how the atom is put together. We talked about how the nucleus, the model is the nucleus, and the neutrons are in the center, and then the electrons are orbiting around the nucleus. Now, we didn't really understand how the electrons were situated, but then further modeling and further data tells us that these electrons exist in very specific energy levels, okay? And so we got into, let me back it up one more. We talked about the energy levels. Now, level 1, level 2, level 3, etc. Those correspond to the periods that are on the periodic table, okay? And notice here, I have the periodic table that we use, and I wrote on the far left, numbers 1 through 7. Some periodic tables have that. No, this one didn't, I have to write it in there. And so we got 1, which goes across. Let me highlight this to make sure we all understand we're talking on the same page. So period 1 encompasses hydrogen and helium, okay? And period 2 starts with lithium, far left, goes all the way across to neon. And I'll do one more just to further demonstrate. We'll make this blue color. Period 3 starts with sodium, number 11, goes all the way across to argon, okay? And so these periods correspond to the different energy levels. And so you can see we have 7 energy levels. Those are the 7 energy levels at the last one here. Number 7 goes all the way to element number 118. When we discover element 119, guess what? We're going to have period number 8 starting in the next group, okay? So with that in mind, let's go back. And we can see here, starting with the first level, which corresponds to period 1. And like I stated, if you take that image and flip it upside down, so it's really, you're building up in like an upside down pyramid. So you're at the first level, working your way up. So the first level, there's 7 energy levels. Now within the energy levels, there are what we call sub-levels, but we use the term orbit, okay? So in the first energy level, there's only one orbit, and that is the S. There's 4 types of orbits, S, P, D, and F, okay? In the second energy level, there's only 2 types of orbits. That's the S and the P. Now, within the S, there's only one S type. That's it, just one. That little box represents one S. Each little box represents an orbit. The P orbit, there's 3 of them. The P, there's 3, hence there's 3 boxes, okay? Now, when we go into the third energy level, which is the third period on the periodic table, we still have an S. Everybody has an S orbit. You can see that from 1 through 7. The P is introduced in the second energy level or the second period. And now at the D, we introduce the D orbit, okay? And in the D orbits, there are 5 D orbits, 5, and hence 5 boxes there. Now, in the fourth energy level, which we're going to stop, but we're going to not go any further, but it also demonstrates, I want to demonstrate here, show you that we introduce the fourth orbit, the F, and there are 7 orbits, okay? 7 orbits. Now, each box can handle 2 electrons. Each box, each orbit, that box represents the orbit, can handle 2 electrons. So when we start off, and I'm going to have here the arrow, which represents an electron. And so hydrogen, number 1, has 1 electron. So I can put that in the first box in the first orbit, and it is 1s1. 1, the coefficient 1 represents the energy level. S represents the orbit. And then the superscript 1 represents 1 electron. And that is hydrogen. As we go across the periodic table, we go to helium. Helium is element number 2. Okay, it's got 2 protons, and guess what? 2 electrons. And so we put its electron in the same orbital in the S, because it can handle, the S can handle 2 electrons. And I put them in different directions because when these electrons orbit, they orbit mathematically. The mathematics tells us they got to orbit in opposite directions. Okay, and that's hence I got the arrows going in opposite directions. So now those are the electrons for the helium. Look at level 2. As you wrap around the periodic table, you go to lithium. Lithium is element number 3. Lithium has 3 electrons. The first 2 are filling the energy level 1, so that's 1s2. But then the next electron, guess what? It goes, we fill up S, P, D, and F. That's the order that you fill them up. So we fill the first electron of the 3 electrons into 2s1, 2s superscript 1. Now, think about this for a moment. If we look at the periodic table, okay, everybody in group 1, we put them all together. And we put them all together because all of them have in the outermost shell 1 electron. Hence, relate that Roman numeral 1 with 1 electron. Hydrogen has 1 electron, that's it. So its outermost shell has got 1 electron. Lithium, we were doing, has 3 electrons. 2 of them are in the innermost layer, 1s, but the next one goes into 2s. It's in the second period. Okay, so it has 3 electrons. 1 of them is in the outermost shell. Sodium, next one down, has 11 electrons. Its outermost shell is in the third energy level. And that's a 3s1. So see how they all have in common? 1 electron in the outermost shell. And they go in that column because they react very similar. Remember, all the action occurs with the electrons, everything on the outside. You know, you cut into something, you know, you don't cut from the inside out, right? You're cutting outside. Obviously makes common sense, right? You cut outside. But that's where all the chemistry is happening, on the outside layer, where all the electrons are. It's all about electrons. So everybody here, even though they have a variety of different number of electrons, what they all have in common is that 1 electron is in the outermost layer. If we move over to the next group, Roman numeral 2, guess what? How many electrons do you think they have in their outermost shell? 2. Okay, they have beryllium, number 4, has 4 electrons. 2 of them are in the innermost shell in the first layer, but in the outermost shell, 1s2, or excuse me, 2s2 is the 2 electrons. Okay, take a wild guess. Let me see. What does your intuition tell you about group 3A? How many valence electrons do you think they have?
3.
You got it. Okay. And now let's go one more. What do you think these guys have in their outermost shell?
8.
8. You're correct, except for one helium. Okay. Except for helium. Helium only has 2 electrons total. Okay. And so it doesn't have 8. So I overdid my boundary with my box here. So it has 2. So I'm going to put him in a special little different color box. He has 2 in the outermost shell. Now the drive is for all the other elements, every one of the other ones, when they get a chemical reaction occurring, to have 8 electrons around their outermost shell. We're going to learn about that. That is the drive for chemical reactions. Because with the magical 8, there seems to be a state where those elements are stable. Your book uses a lot. They're happy. If you want to put emotion to it, that's fine. But they're stable. And so the drive is to gain or lose electrons such that their outermost shell is like the noble gases. That last column are called noble gases. They're called noble gases because they don't react with anything very readily. And they don't react because they happen to have 8 valence electrons and they fulfill the octet. Helium has its own little rule. Helium's just got the duet rule, the 2. Everyone else is the octet. Okay, so excuse me. So we went through this scenario of demonstrating all these orbits, and there's a question. Okay, good question. Let me go back to the periodic table. Now, the B elements, those are the ones with the Roman numeral B. They're going to have it called transition. You're going to learn their name later on, but right now I just highlight them. Okay, we cannot predict the same with these guys and with these guys like we did with the A, the Roman numeral number 1 through 8A. They have a variable system. We're going to learn that pretty soon. For example, iron. Iron has the capability in existing in 2 forms, and it's by either losing 2 electrons or 3 electrons. Copper, wrong one. Copper, sorry, has cobalt. Copper right here, Cu. There's 2 forms of copper also, copper 1, copper 2. So they vary depending on the reaction conditions. So we can't predict how many valence electrons they have on their outermost shell or the B elements at this point in time. We will learn how to do that, figure that out later on. But for the others, the A's, the Roman numeral 1 through Roman numeral 8A, no question there. By looking at what group they're in, you know how many valence electrons they have. Okay, so going through this scenario, we went through figure out the electron configuration. Okay, this is a description of the electrons of the element and how they are placed together with respect to their orbits. Okay, that is what is demonstrating. And there's a couple of things you can take away from this is that it also, let me back up. It also demonstrates the valence electron. If we look at sodium, its electron configuration is 1s2. Remember, the coefficient is the energy level. The letter is the orbit, okay? And the superscript represents the number of electrons in that orbit. Recall that the p orbit, there's 3 p orbits, and each one can handle 2. So there's a total, when you max out the p orbits, you got 6, hence the superscript 6. The 3 for sodium is the outermost shell. If you go look at the periodic table, you'll see that sodium, guess what? It's in the 3rd period, okay? It's in the third period, and top it off, on top of that, it's in group 1. So that tells you, oh, 1 valence electron. Here's the electron configuration to demonstrate that. The last electron, the outermost shell, is in the third period, and that valence electron all by itself is 1 sitting up there. Now, if we go look at oxygen, its valence shell, if we look for oxygen, oxygen's number 8. It's in the second period of number 8. It's in group 6A. Group 6A tells you I got 6 valence electrons, which is consistent with the electron configuration. Those 6 valence electrons are in the second period. Hence, we have 2s2, 2p4. 4 plus 2 is 6 valence electrons. Okay? Go to calcium. Calcium is in the fourth period in the periodic table. And it's in group 2A, which tells you I got 2 valence electrons in the fourth period. All the other electrons are full, all those electrons. Hence, we got 1s2, 2s2, 2p6, 3s2, 3p6, and then finally 4s2. And then here's another thing. Look at chlorine. Note, first of all, the name chlorine. C-L-N-E is the ending. Its valence shell, its valence energy, the valence electrons, there's 7 of them. It's in group 7. And chlorine is in period 3. Okay? Now, chlorine has a total of 17 electrons. Of those 17, 7 are in the outermost shell. And the rest of them are in what we call the core electrons, the next layers in. Okay? So we're just building them up. Now, a couple of things I hope you can pick up from here. Now, if you look at sodium, it's got 1 lonely electron sitting out there. Now, it has a choice here. It can pick up the S, the P, and the D. So we're looking, the D can handle 10, the P can handle 16, 17. I need 17 more electrons to fill up that third energy level of sodium. Now think about it from an energy perspective, or from your own thinking. Will you think it would be easier to pick up 17 electrons or get rid of just that one sitting there all by itself?
Get rid of just the one.
Exactly. You know, it's analogous to I got 17 kids, 18 kids. I'm trying to get them into into a truck or a bus. I got 1 in there. It was easier to get 17 in there or get 1 out. Okay, rather than try to gather everybody else up and get them in the bus. I know this because I had 7 boys and I had a van. It was fun on trips. Anyway, so to get 1 out, so 2 things. Sodium is a metal. Okay, remember we have metal, non-metal, metalloids. And at that time I may have said, but if not, I'm telling you now, put this in long-term memory. All metals want to lose electrons. Okay, again, all metals want to lose electrons. The converse of that is non-metals. All non-metals want to gain electrons. So we see we got sodium here, which is a metal. And if you forget who's a metal, who's not, look at the periodic table and look at the stair step. To the left of the stair step are the metals. To the right are the non-metals. On the stair step are the metalloids. And so sodium metal, the elemental sodium, will want to lose that 1 electron sitting there all by itself. And guess what? When it does that, that 3s1 now is empty. And the valence shell, the new valence shell, is the next one in, which is in the second energy level. And guess what? There's 8 electrons in the next layer. Is full, which means it has the same number of electrons as a noble gas. Now, by losing one electron, does sodium change with respect to charge? Okay, because sodium begins with 11 protons and 11 electrons. Now I lose it. I got 10 electrons and 11 protons. What is my net charge? 11 positives, 10 negatives. What's my net?
It's a negative charge.
Let's think about it. No,
I'm sorry, positive charge, positive.
you got it. Okay, exactly. I got a positive 1 charge. So what has happened is by losing that 1 electron, now I have created what's called an ion. And that is what you're putting on your French fries. You're not putting sodium metal on your French fries. That sodium ion is what's happening in your heart. The ion is there to assist with your heart contraction, electrical nerves moving from point A to point B. It's the ion, and 1 tiny electron is lost. So that's what you put on your French fries, not the sodium metal. Now, let's go on the other end of the spectrum. That's sodium. Let's take a look at chlorine. Okay. Now, chlorine in the outermost shell has 7 electrons. So what do you think would be easier to do? Get rid of those 7, or maybe just plop in 1, right? Which one do you think would be easier? From an energy.
Positive 1.
Yeah, exactly. Because by adding 1, you see the 3p5 has room for 1 more. 1 more electron. So it could easily drop in that 1 electron right in there. And when that occurs, its electron configuration now. Okay, we'll have this be clear here in a bit, but this will be a 6. I know I'm looking at. So that'll be a 6. And guess what? What do you think his new charge will be? If I gain one electron, what do you think my charge would be?
Negative?
Exactly. It'd be negative. Okay, it's a hyphen. And this is also the ion. And they're going to have their own little names. Right now, we're going to call them ions. Okay. Guess what happened to the name? Oh. Chlorine, INE, when it becomes an ion, we change the name to chloride. Okay. Now, if you use fluorinated toothpaste in the morning, you're not brushing your teeth with fluorine. You're brushing your teeth with fluoride, IDE, which means you're brushing your teeth with the ion that gain an electron. Okay. Excuse me. So what's happening here now? This is a nonmetal. Remember I said nonmetals gain electrons? Here's an example. It gained an electron, and now in the octet, excuse me, the valence electron shell is full. It's got a negative. I got 6 electrons. It is happy, as the book calls it. It is stable. And now we change the name to chloride. And so what you put on your French fries is the sodium ion, the sodium, and the chloride, which is the ion. Okay. And it's all about electrons here. All right, we'll get some more examples here. So it's the electron configuration. Now, in my periodic table, I put in the names. Think of the first group 1 and group 2 as the S electrons. Think of what's in the yellow as the P electrons, and then in the D are sitting there in the middle, and then the S. Now there are 2 columns for the S elements. I didn't say electrons, I meant elements. There's 2 columns. Guess what? S1, S2. In the D, there's D1 to D10. Remember, D can handle 10 electrons. In the P, there are 6 columns, P1 all the way to P6. Okay, I got a question here. So because just the electron, yes, you are correct. When you move or take out or remove protons, you change the element, which is not a good thing to do because that's called nuclear fission. It's called big boom, okay, because it's in the nucleus. But you change the element. And earlier when we were talking about that, we can change neutrons and electrons all day. We can add them, subtract them all day long, but you don't change the element. What you do is by adding or removing electrons, you produce the ions. And these ions are either going to be positive or negative, depending if they lose or gain electrons. Okay. And those are the guys that actually are what you're ingesting. So next time you drink some Pedialyte, have your kids drink Pedialyte, what you're drinking, ingesting are the ions of the elements. These are the ions that have lost or gained electrons, because that's what your body needs. Your body needs iron. You're not ingesting a chunk of metal, the element. You are ingesting the ion of iron, either iron 2 or iron 3. Okay, because iron 2, iron 3 is right here. And earlier I had the question about the charges, because iron's right there, and iron exists either as iron 2 or iron plus 2 or iron plus 3. Okay. All right. Where are we at? All right. So this table here helps you with the electron configuration. You'll see here, if I start in the top left corner, that's hydrogen. So its electron configuration is 1s2. I go across to the far right corner of the table, I get 1s2. Guess what? That's helium. Okay. And so if I wrap it around and I go to lithium. Now lithium would be 1s2 and then 2s2. Excuse me, 2s1. Lithium is the first yellow one in the top left corner. Okay. So its outermost shell is in the second energy level, and I only got one electron. So the innermost is 1s2, and then I write down 2s1 for lithium, and so forth all the way across the periodic table. Now, if you look at the D electrons, you may notice that it's not consistent. So it goes across from left to right. It hops around, goes 3 to 5, 6, 7, 8, and then jumps to 10. For our purposes, for right now, it's just simply D1 across sequentially to D10. Okay, and the same is true for the F. So sequentially, starting from F1 in the first column all the way across F14. Multiple reasons why it hops around, but we're not gonna work on that. But do notice this, number 21, element number 21, which, let me change the color here. Scandium, which is right here. Okay. Remember I said that the D elements, you don't need to worry about them until you hit number 21. Okay. So there's 21, I circled it. If you look at the periodic table, okay, it's SC. So the D elements, the D orbitals begin, but they begin energy level 1 from the period they're in. What I circled is in 4 periods, but the D orbits are actually in the 3rd energy level. Hence, it's 3D1. Then the same is all the way across. The same is true for the F. Okay, the F elements, which don't really kick in until you get to number 58 there, they're in the 6th period. But the F orbits, energy-wise, they don't begin, they begin with the 4th energy level. Hence, you see 4F. Okay. So this one so you can use either the top or you can follow the sequence given to you, the order 1s2 down here at the bottom. Okay. 1s1, 2s2, or use the periodic table. I prefer the periodic table because I can very quickly, just by knowing its position on the periodic table, just write out the electron configuration. But it takes a little practice. Work on the first 20, and then if you need assistance, I'm sure, yeah, we'll bring it to class and we can go over some examples. Okay. All right, so I mentioned about noble gases. They're all stable. and quote happy, right? And that's because their outermost valence shell is full with that magic 8. Okay, with the exception of helium has its magic 2. Okay. And that's in that outermost shell would be the S2P6, 8 valence electrons in the valence shell. And the strive here is for elements to obtain their valence shell like a noble gas. I repeat, their strive is to have their valence shell be like a noble gas. They won't be the noble gas. I didn't say that. The ions are not the noble gas, but they share the same number of valence electrons. Okay. That term used is called isoelectronic. Iso meaning the same. We're going to have some examples of that here in a bit. But I want to emphasize again the valence shell. You can see here phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. Now, if you look at the periodic table, phosphorus is in group 5, 5a, Roman numeral 5a. Okay. That tells you I got 5 valence electrons. Look at the diagram here. I got 5 valence electrons. Okay. Both 2 of them are in the 3s orbital, and 3 of them are in the 3p orbital. Now, what would be your guess with respect to phosphorus? Keep it in mind 2 things. 1, it's a nonmetal. 2, it has room for 3 more electrons. Do you expect it to lose or gain electrons? What do you think? Remember about the cardinal rule about gaining and losing electrons, depending if you are metal, non-metal? What did I say about the non-metals? Would they lose or gain electrons?
Gain electrons.
You got it. They will gain electrons. Look at phosphorus on the periodic table. It is number 15. It's a non-metal. It's in group 5. It's very close to the noble gas, and it can be like the noble gas as far as electrons by simply gaining 3 electrons. And second of all, does it have room to gain 3 electrons? It sure does. Because if you look at the valence shell, okay, right here, it's P3. Remember, we can put 6, a maximum of 6 in the p orbit. So it has room for 3 electrons. All right. So phosphorus, when it picks up 3 electrons, now it becomes P superscript 3 minus 3 charge. And guess what happens to its name? Phosphide. The ion is called phosphide. The element is called phosphorus. Okay. Now, getting the hang of the naming is important because down the road we're going to get like a sentence or two about a reaction, and there's a difference between writing phosphorus versus writing phosphide. Just like there's a difference between writing chlorine versus chloride. Okay. Question? Yes, the IDE always means the ion. Okay, the ion of the nonmetal. And so we can let me go up to the periodic table. Okay. Now, let me highlight that. Right here. So nitrogen, oxygen, and fluorine, when they become ions, nitrogen becomes nitride, oxygen becomes oxide, OXIDE, fluorine becomes fluoride. Okay. phosphorus, sulfur, and chlorine. Phosphide, sulfide, chloride. Okay. And you can do the selenide, SC, and bromide. And iodide, because Te is a metalloid. So those are the main ones you're going to be working with. Now you might ask, oh, what about carbon and silicon? Here's the thing with these guys, group 4. Okay, group 4, they're on the fence. Okay, the magic number is 8. So in group 4, it can either lose 4 electrons, or guess what? It can pick up 4 electrons. So carbon and silicon, depending on the reaction conditions, can lose or gain 4 electrons. In group 3 and back, 3, 2, and 1, they're going to lose. They're always going to be a positive. But group 4 guys are right on the fence. And depending on the conditions, which when we talk about it, you'll be told. Okay. So it can lose 4 or lose 4 electrons or gain 4 electrons. All right. Let me go back to this. So valence electrons for chlorine, beryllium, and aluminum, we simply look for them on the periodic table. Okay. We can see that chlorine's in group 7 and therefore has 7 valence electrons. And there's the electron configuration. 3s2, 3p7 is the valence shell. Okay. Beryllium is in group 2a. 2 has 2 valence electrons. Its electron configuration is 1s2, 2s2. And aluminum, okay, aluminum is in group 3. Has 3 valence electrons. Now, who can tell me aluminum? Do you think aluminum is going to gain or lose electrons?
Lose.
Lose.
50-50 chance here. Okay, what is aluminum? First, ask yourself the question. Aluminum, is it a metal or non-metal?
Metal.
A metal. And what did I say about metals? 100% of the time? As
Lose
far as lose electrons, okay? So aluminum will lose electrons. Now, once it loses electrons, can anybody tell me, based on the electronic configuration, what is its final charge?
Negative.
Okay, it's going to lose electrons, negative. What is its final charge? Well, how many valence electrons does aluminum have?
1.
Oh, no. What
No.
group is it? 3, yes. What group is it
3.
in? Okay, it's in group 3. Okay, it's in group 3, and therefore we'll lose 3 electrons. Let me highlight that. Okay, that's the valence shell, remember? Aluminum is in the 3rd energy period level. So those 3 electrons on the outermost shell, that's its valence electrons, 3 of them, and they're in the 3rd energy level. It's going to lose those 3, okay, because it's a metal. And when it loses those 3, what is my final charge?
Negative.
Oh,
-3.
no.
A +3. Positive. So, okay,
Yeah.
it would be 3. You're okay. Yeah,
Which one?
it is positive, right?
It'll be positive,
It's the 13 minus 10,
which it would be, what's the final charge?
so +3.
You got it.
Okay.
Okay, think of it this way. Think of it in human terms, if this helps you. I lose negativity. Do I not become a positive person? Yeah, electrons are negative, right? And the reverse of that, if I pick up negativity, don't I become a negative person? And so if I pick up negativity, overall, my new overall personality is negative. If I lose negativity, my overall personality is positive. If aluminum loses 3 electrons, now it has a net charge of a positive 3 because it lost 3 negatives. Okay, so aluminum has a positive 3. Now it's important that we know this because we're going to be putting these together. I'm going to take aluminum plus 3 and then I'm going to combine it with chloride -1. And I have to put them together such that the positive, enough of each, so the positive and the negatives cancel each other to make a compound. Okay, so it's important that we learn the charge of these ions, of the metals and the non-metals. For the ones in the B, you'll be told some more information because, like I stated, they're variable. And we'll
So
get-
if the element is losing electrons, you will become positive. It will become positive, and if it's gaining electrons, it will become negative. That's how it always works.
you got it, 100%.
Okay.
Okay. So, and metals always lose electrons.
So
That
metals always become positive.
got it. And non-metals always gain electrons. So what do they become?
Negative.
Negative. Okay. In fact, let me see. Give me 1 second. I'm going to pull up another periodic table. Okay. All right. Here's a periodic table, which I've highlighted. Okay. With the group 1, this is just the metals. We'll get to the non-metals in a second. Okay. The metals, in which I put a circle in there. Hydrogen is not a metal. So even though it's in group 1, you can remember it's not a metal. And so starting from lithium on down, those all have 1 valence electron, and therefore when they lose that 1 valence electron, we'll have a +1 charge. Everybody in group 2, when they lose those 2 valence electrons, will have a +2 charge. Every one of those guys. Okay, those you know 100% of the time. But there's 1, 2, 3, 4, 5, 6. There's 12 elements that you know 100% of the time what their charge will be when they become ions. Okay. Now, on top of that, we got 1, 2, 3, 4, 5, 6, 12, 13, 14, 15, 16. Yes, right, 16. These other metals, when I put in blue here, that is aluminum, zinc, silver, and cadmium. Aluminum, 100% of the time, will always have a +3. Zinc will always have a +2. Silver will always have a +1. CD, or called cadmium, will always have a +2. So there's 16 elements. Remember, there's 118, but there are 16 metal elements that you would know their charge 100% of the time when they become ions. All the other metals vary, okay? They vary in charge, and it's difficult to determine what they would be unless you're given more information. Everybody in group 1, group 5A, they're non-metals, so they're going to have a -1. So nitrogen, let me highlight that. So these guys, and then let me change the color a little bit. And then these, and then these. Okay. When they become ions, the first group in red will have a -1 charge. The next group will always have a -2. Whoa, whoa, whoa. I'm going the wrong direction. -3, comma, -2, comma, -1. Okay? And so nitrogen and phosphorus, when they become ions, will have a -3. Why? They're in group 5. They pick up 3 electrons. Oxygen, sulfur, and selenium will always have a -2. Why? Because they're in group 6. They pick up 2 electrons. And fluorine, chlorine, bromine, and iodine, they'll always have a -1. Why? They're in groups 7. They need 1 electron. Okay. And so now you know 1, 2, 3, 4, 5, 6, 7, 8, 9 elements that when they be non-metals, that when they become ions, you know the charge on these ions 100% of the time. Okay. Eventually, we're going to take those negative ions and we're going to combine them with the positive ions to create compounds. Okay, so I take sodium, had a +1, with the chloride has a -1. I put them together. Its formula is NaCl. Okay. All right. Let me go back. So yes, we do need to become okay with finding out the charge in them. For example, with respect to just valence electrons, the Roman numeral up there on top of the periodic table for the A elements gives you how many valence electrons. That's it. With the exception of helium, I've got to overemphasize that because sometimes people say helium has 8 valence electrons. It doesn't. It only has 2. Okay, let's not forget about helium. And so I can very quickly go to the periodic table and any of the A elements determine its valence electrons. So strontium has a group 2. In group 2A, so it has 2 valence electrons. Bromine has 7. Argon is a noble gas, has 8. Silicon has 4, just like carbon does. And sulfur has 6. So no need to memorize it, just to find it on a periodic table and find out what group it's in. But if you feel comfortable with memorizing these numbers, by all means, go ahead. Now, what is the driving force here? The driving force, hold down 1 second. All right. Is atoms, when something happens to them chemically, they are striving to get what we call the octet fulfilled, the 8, and is striving to have a electron configuration like the noble gas. Now, with respect to metals, when they lose electrons, they have the electron configuration of the noble gas behind it. And so sodium, when it loses 1 electron, now has the electron configuration of neon, the gas behind it. Chlorine, by picking up an electron, now has the electron configuration like the noble gas in front of it, which is argon. Okay. And they're striving to have the electron configuration. When they lose and gain electrons, they form what I just talked about, an ion. Okay. Let's take a look at sodium. Sodium, its electron configuration is 1s2, 2s2, 2p6, and then its valence shell, 3s1. We talked about this earlier. Okay. Sodium, being a metal, is going to lose an electron, and it's going to lose the one that's hanging out there all by itself. Okay. It won't lose any more. It won't lose any from the second energy level because it's full. That's a stable state. So when it does that, that 3s1 orbit is empty now because it lost an electron. Also, keep in mind that it now has a positive charge. Okay, superscript positive, because it lost that 1 electron. So now it has 10 electrons. Sulfur, and the other end of the spectrum, it's a non-metal. So it's going to gain electrons. Now, its valence shell, its electron configuration is 1s2, 2s2, 2p6, and then we got 3s2, 3p6. It is in group 6. Sulfur is in group 6. Being in group 6, it has 6 valence electrons. Notice how the periodic table is our model with electrons is fitting with the elements and where they are in the periodic table, and also why reactions occur. I mean, why they act a certain manner based on their position in our periodic table. Okay, and so it has room for 2. In the p orbit, there's room for 2. There's 4 of them right now. So it will readily pick up 2 electrons because that is the most stable state. Okay, and by that, now it has 8 valence electrons in its new valence shell, which is still the 3rd energy level, but it's full now. Okay, now let me ask you guys here for a second. Given this information we have now, I want you to kind of take this information and extrapolate, conclude something from it. Okay. Now, if we look at the sodium element and we look at the sodium ion, they have a radius. Okay. Now, just for sodium ion and sodium element, after the sodium element has become an ion, do you expect its radius to be greater, smaller, or no change? The radius,
Smaller?
pardon me?
Smaller?
Exactly. Because the sodium, remember, its outermost shell is the 3rd period. It's bigger. And when it loses that electron out there, now the radius is the next one in, which is the 3rd energy level. So you're correct. When the element becomes the positive ion, the radius of the atom decreases. What could you say about the other way around? When it gains an electron, would you expect the ion to be, same question, would it be the same, would it be less, or bigger?
Would that one be the same?
Well, think about this. It picked up more traffic. It picked up 2
Okay.
electrons. Yeah.
I guess the reason why I was wondering if it was the same is because it's picking it up, but it's still in the same level 3.
Yes, it's picking, and it's a little bit confusing, and Samara has it correct. Yes, it gets bigger because now remember, it starts off with 6 electrons, okay, which are negative. And now I put in more electrons, which are negative, and they're going to repel each other. So now I got more repulsive force in that orbit. And so the electrons are going to want to push away from each other because I got more traffic, more electron traffic in there. And so their radius gets bigger, okay? Simply because we added more electrons. Even though we're in the same energy level, we're adding more traffic within that energy level, and they're going to repel further apart. It would be analogous to having 6, let's say, 6 magnets, north to north, all repelling each other. And then I add 2 more in there, north to north, repelling each other. They're all going to want to repel further apart because we added more forces in there. Okay, so pardon me?
Oh, I just said, okay.
All right. And so when an element becomes a positive ion, the radius gets smaller. When it gains an electron, the ion gets bigger. Okay. And that's a trend that we're going to be looking at later on down the road. All right. So here they're asking you to write the electron configuration. Now, what I've seen in the past is students put the electron configuration, but they put it in for the element because they didn't look at what they're given. And you can see they got potassium with the +6. So we're talking about the ion. All right. And what students would do is write the electron configuration for the element. And so they would write potassium would be 4s1. That's what they will put in there. Well, that wouldn't be the electron configuration for the ion. It'd be for the element. 4s1 would be the element, the atom itself that loses that one electron. Nitrogen picked up 3 electrons, becomes nitride, and then magnesium, being a metal, being in group 2, lost 2 electrons. So it becomes +2 ion. Notice the similarities here, okay? For between nitrogen, which was called nitrogen, now is called nitride, okay? That when the negative charge ion of nitrogen gains 2 electrons, and when the metal magnesium loses 2 electrons, in both cases, the electron configuration is now the same as the noble gas neon, okay? And now they're a lot more stable. All right, I should add here, this is called nitride. Oh. Ion. Okay, so when oxygen becomes an ion, nitride. Nitrogen, when oxygen becomes an ion, it becomes oxide. Whoa. All right, so where are we at? 38. So these are the ionic charges we're talking about. We said, I told you earlier in that periodic table, group 1 and group 2, they're always going to be a +1, always going to be a +2 ion. And the ones in group 3 will be a +3 ion. Those are the metals. All those guys are metals. Those are their respective ions, okay? It's understood, for example, if it just write the plus, it's understood to be a 1, just like mathematics. So you don't have to put a 1. That's what they're striving, telling there, be it positive or negative. You just put the plus or the hyphen in general, unless there's multiple charge like +2 for magnesium. Now, whether you write it +2 or 2+ makes no difference. It's the same thing. Okay, multiply 1 times 2 or 2 times, it's the same thing. All right, so what group does group 7 want to do to be a noble gas? Well, to do that, it wants to pick up 1 electron. Okay, group 6 wants to pick up 2 electrons. All right, and group 5 will want to pick up 5 electrons. I don't think this has it here. So as I stated before, nonmetals, put this in long-term memory, nonmetals want to gain electrons, and by gaining electrons, they become negative ions. Negative ions have their own little name, okay? They are called anions, okay? Anions. Before we just called them negative and positive ions. Now we're being more specific. Anions are negative charge. So the chloride, the bromide, the nitride, the oxide ions, those are collectively anions. Okay. Group 7, -1 charge. They pick up 1 electron. Group 6, they pick up 2 electrons. They have a -2 charge. And group 5 pick up 3 electrons with ending up with a -3 charge. Okay. Not only that, they also change their name. Let me clear that. They get a name change. It's only the elements in the non-metal elements that when they become anions, they change the name. The metal cations, which is what we're going to show you here in a second. The metal ions, their name stays the same. I tell you this because we're going to have a whole chapter on nomenclature, which is nothing more than name that compound. Okay, metals lose electrons and therefore become ions. their general term or their specific term is a cation right here. So anions are negative, cations are positive ions. Nonmetals gain electrons, like I stated, they become anions. So that way there's no question with respect to negative positive because the term ion is general. We don't know, you tell them positive ion or negative ion, but with the term cation, there's no question it is just a positive ion or anion. It's a negative ion. Doesn't tell you the magnitude, +1, +2, it just tells you it's a plus charge. And having a plus charge, remember, it's a plus charge because it lost electrons, which are negative. So their net charge now is positive. It's a negative charge because it gained electrons. Now the net charge is negative. Okay. So what about group 4? Well, like I explained earlier, they got 4 valence electrons, carbon and silicon. They can lose 4 or gain 4. So their charge could be a +4 or as far as a -4. Depends on the conditions they're on the fence. Okay. And obviously group 7, they're stable. Nothing is going to happen to them because they will they got the octet rules fulfilled. Okay. So across the board, this kind of helps you out there with that. +1, and this is again for the A elements. +1, +2, +3. Group 4 can go depending on what the conditions are, +4, -4. And then you jump into -3, -2, -1. And then obviously the group 8 are noble gases, okay? Across the A group. Let me clear this up here. So when we look at here, look at these, they're asking you what charge ion would they become? Well, to answer these type of questions, you got to know 2 things. One, is it a metal or a non-metal? Okay. And then 2, where are they with respect to the periodic table? Because that would tell you what their charge will be. Okay. So if we look at lithium, lithium is a metal. It is in element number 3. It is in group 1. Okay. Therefore, it has 1 valence electron. Being in a metal, it's going to lose that outermost shell, the outermost electron. And so it's going to have a +1 charge. And we write it, the ion will be Li superscript positive. Magnesium. Same scenario, you do a systematic approach until you become comfortable with it. Magnesium, find it in the periodic table, it's to the left of the stir step. It means it's a metal. Being a metal, it's going to lose electrons. Find its position, what group it is group 2A, therefore has 2 valence electrons in the outermost shell, the valence shell. So therefore, it's going to lose those 2 and therefore has a +2 charge. Okay. Sulfur, same scenario. We find that in the periodic table, it is a non-metal. It's a non-metal, it's going to gain electrons. It is in group 6. Being in group 6 means it will gain 2 electrons. Therefore, we'll have a -2 charge. We can add more information on there and also write in there that its new name, keep that in mind, is now sulfide. Because remember, the anions are the ones that changed their name. All right, next one up is bromine. Bromine is a nonmetal. It's in group 7, okay? Therefore, it would gain 1 electron, and therefore it has a -1 charge, okay? And it went from bromine, the name bromine, to, guess what? Bromide, okay? Nitrogen, another nonmetal. It is in group 5, which means I'm going to pick up 3 electrons, which gives me a -3. Okay. Being a -3, its name, and it's because it's an anion, now becomes nitrite. Notice nitrite is much different than nitrogen. And then we have aluminum. It's a metal, which means it will lose electrons. We find it in the periodic table. It is element number 13. Yeah, group 3. Okay, meaning it's going to lose those 3 valence electrons and therefore have a +3 charge. Okay, now what does this all mean? Well, this means that we're going to put them together eventually. We're going to combine the lithium ion, the lithium plus, with, for example, the bromide. Okay, we're going to put them together such that they're equal with respect to the charges. Now, lithium ion has a +1 charge, and the bromide has a -1 charge. One positive, one negative, they cancel each other out. So I can use one lithium and one bromide. And guess what? Its name is, its formula is LIBR. I put them together without the charges. And its name is lithium bromide. Not lithium bromine, because bromine is the element. Bromide is the ion. Okay. Now, if I put together magnesium with the sulfide, magnesium has a +2, the sulfide has a -2. So I can very safely put one of each together. Okay. And name them magnesium sulfide. This is just the beginnings of nomenclature, because eventually you can be given either the name and asked to be given the formula, or I can give you the formula and asked to give you the name. Okay. But
Do
you have
you
a
not
question?
write the 2+ and the 2- because they cancel each other out, or because you just assume that, or because they're the same, like they're
No.
both 2?
Exactly. No assumption here. The fact that you got a +2 and a -2 on each one, when you put them together, they cancel each other out. Now, when they're not the same, guess what happens? All right. So let's try magnesium and bromide. Okay. And so we know that magnesium, we know we're going to use one magnesium, but the bromide, okay, is a -1, right? So how many bromides do I need to cancel that +2 of the magnesium?
2.
I need 2. And this is where you put in a subscript. I can't write the subscript, but that's a subscript, okay? All right, the superscript I can do with my little caret, but this is when I put the formula together for magnesium. Guess what the name is? Bromide. And that is the formula. And there's 2 subscripts. Remember way back when we said when atoms come together, they come together in whole numbers, either 1, 2, 3, 4, 5. Well, here to make magnesium bromide, I need 2 bromides for every magnesium ion, because the magnesium ion has a +2 charge. Okay. All right. So what would you say if I put aluminum and bromide together? How many bromides would I need?
3.
Exactly. I would need, if I were doing aluminum with the bromide, then a subscript would be a 3. Okay, that's a subscript, because I got 3 bromides. I got to put them together to cancel the +3 of aluminum. But more on that later on. We'll be doing a lot of that. And even right now, based on this, you can mix and match, knowing of all the ions in group 1 and group 2 and the negative ions that we talked about. If you put them all mix and match, you can probably come up with maybe a couple hundred different compounds already at your access that you can put together. Okay,
I have a quick question.
sure.
Now, for right now on the, on these elements that you gave us the example, for the superscripts, the 2 positive, the 2 negative, on our notes, there were a couple of times it was different. So it would be magnesium negative and then the 2 for the superscript. Now for like our test, does it matter where the positive or the negative goes, if it goes before the number in the superscript or after the number?
Oh, no. Like, right here, let me back up. In fact, I mentioned that, right? Where'd it go? There was one that I.
There
put
was one right there. It was positive 1 and then the 3 negative. Does it matter?
No, it does not matter. It does not
Okay.
matter. You got a negative up front or you put the negative afterwards. It makes no difference whatsoever.
Okay.
Okay.
Thank
No
you.
difference. Yeah, no problem. And I think, where was I? I think we're like 2 pages away. You're almost done. Okay, we got that. All right. Well, I tell you what. Let's forget it. I'm going to stop it here on page 43. How's that? And what we'll do on Tuesday, we'll continue with, finish this up and then jump into chapter 5. Chapter 5 is a short periodic table chapter. Won't take long. Some of the stuff we already introduced. I try to introduce stuff to you early, so when you see it, it's not like, well, it's a surprise. You're like, oh yeah, I remember this. Okay, hopefully make it clearer to you when we get to it. So let me see.